Good morning, everybody. Today is an early release day. For first period, we get out at 9:25. So I'm going to go ahead and start with the notes already. We're starting a brand new unit, mechanical energy, and then you have some discussion questions after the notes. Not too hard. So mechanical energy. First, we need to understand the relationship between work and energy. When you do work on an object, you change its energy. So anytime you're doing work on something, you're changing the energy of that object. Energy is the capacity for doing work. That means you're able to do the work. And the unit for energy is also in joules, just like in work. So work and energy have the same unit. They are both measured in joules.
Just had a spike of myself.
Huh?
So sometimes I feel a random cold spike and my body just starts shivering.
Ooh, the
It's
glitch in the
fine.
matrix.
It's fine. It usually stops like immediately after. Like it's there for 1 second and it goes away. My brother has it too. It's just something in our family.
Okay. All right. These are the types of energy. We have mechanical energy, chemical energy, electromagnetic energy, and nuclear energy. So we're actually going to talk about electromagnetic and nuclear energy later on this year. But right now, all we're going to focus on is mechanical energy. So this whole unit is just going to be on mechanical energy. And mechanical energy is the sum of kinetic energy, which is the energy with motion, and potential energy, which is the energy with position. So there are two types of mechanical energy. Again, we have potential and kinetic. Kinetic is just in motion. Anytime you're moving, you have kinetic energy. If you're not moving, you don't have kinetic energy. Simple as that. And then there's two types of potential energy. One is gravitational potential energy, and that's going to determine on your height and how far you are away from the Earth's surface. And then the second one is elastic potential energy. So I'm going to show you the formula for both, but really we're only going to focus on gravitational potential energy this year. Just because you're online, it's a lot harder to do everything on a computer. All right, so this is kinetic energy. Sometimes I'll write it as KE, other times I will write it out as kinetic energy, but they both mean the same thing. This is energy possessed by any mass in motion. So again, anything that's moving has kinetic energy. Kinetic energy is energy in motion. It's energy that is doing work. For example, when you push a shopping cart, your work goes into increasing its kinetic energy. The formula for kinetic energy is 1/2 of the mass times the velocity squared. Only the velocity is going to be squared, not the mass, just velocity. We're not going to do any formulas today. Just kidding, I lied. We'll probably do 3 today. But we won't do the hard stuff until tomorrow because we don't have time today. And then again, since kinetic energy is an energy, it's also measured in joules. So this is the formula written out again. This is the triangle if you like to use the triangle. I'll give you some time to write it down tomorrow so you don't really have to look at it today. But I promise you it's pretty easy. We already know mass is measured in kilograms and velocity is meters per second squared. Oh, just kidding, it's not. It's just meters per second.
Acceleration's meters per second.
Acceleration's meters per second squared. Yes, I messed up. Sorry for that typo. Good job though. Yes, acceleration's meters per second squared. Velocity is just meters per second. Oops. Okay, so the relationships in the formula, when we're comparing kinetic energy and mass, they're directly related. So the larger objects are going to have more kinetic energy. The smaller objects are going to have less kinetic energy. Pretty easy to remember. Heavier has more energy, smaller has less. The same thing with velocity. Velocity and energy are also directly related. So the faster something is going, the more kinetic energy it's going to have. If it's going slow, it's going to have less kinetic energy. If it's going fast, it's going to have more. All right, so let's go through this practice problem so I can show you how easy it is. As you are playing a soccer match, a player of the opposite team runs into you. If the player's mass is 62 kilograms and he has a speed of 2.5 meters per second, what is the player's kinetic energy? So mass is 62, velocity is 2.5. Remember, velocity and speed are the same thing, except velocity has direction, speed doesn't, but it can still be the same thing. And then we're looking for our kinetic energy. So to solve this problem, your formula is KE equals 1/2 meters velocity squared, not meters, sorry, mass. Oh my goodness. So 1/2 is the same thing as saying 0.5. However you want to type that in your calculator, you can. I like typing 0.5 more than I like typing in 1/2. It's a lot harder to do 1/2.
Or you can just divide by 2.
Or you can just divide by 2 in the end, yes. Mass is 62. Ooh, my brain is not here today. I'm writing my 2 before my 6.
Wait, your brain always goes with you?
Sometimes.
My brain's always fighting against me. Especially on days like this.
A half day?
Yeah, it's just like, I want to get this over with so I can go to school. No! If you do that, we're going to fail our assignments.
Yes. Okay, so again, I just want to point out only velocity is squared. You're not going to square anything else. Don't square mass. Don't square the half. Just square velocity. Because I don't want you to mess up on anything. So when you're typing all that in your calculator,
Kilograms.
you should get somewhere 193.75. And then your unit for kinetic energy is joules.
I mean, it's basically work, but it's just extra steps.
Yeah, just extra steps.
It's work, but with extra steps.
Yeah. So I just wanted to show you the simple problem. Tomorrow we're going to solve for mass. Tomorrow we're going to solve for velocity.
Oh my God, I just got the answer for the first question of this discussion. What is kinetic energy? Work with extra steps.
All right, so pretty easy for this formula.
I mean, I'm technically right.
Technically. All right, so now we're on potential energy. To lift any object off the floor, you must do work. Once an object is no longer lifting, well, I mean like it's no longer moving, it has 0 kinetic energy. But the work done lifting the ball is not gone. It's just going to be transferred to potential energy. So as you're lifting something up in the air, you have kinetic energy because it's moving. But once you stop, your kinetic energy is gone. It's completely gone. But it just doesn't disappear. That's not how energy works. It just transfers to something else. So if you're lifting weights and you're just holding it up, your arms are shaking because it's hard, right? You're doing something. So that's all potential energy. It's storing that energy because it has the potential to come back down, right? So you're storing all that energy. You're holding, your arms are shaking. You're putting in all that energy. And then once you make it come back down, then it goes back to kinetic energy. So potential energy is the energy stored due to interactions between objects in a system. It's the energy stored for later use. It's the energy at rest. It's the energy that could do work. Like I said, it has the potential to do something. It's not doing something yet, but it has the potential to do it. And there are 2 types, again, gravitational potential energy and elastic. This unit, we're only going to focus on gravitational, but I am going to mention elastic today. So gravitational potential energy is the most common one. This is the energy stored based on its height. So however, how high you are is going to determine how much gravitational potential energy it has. So when you climb a mountain, you're increasing your potential energy the higher and higher and higher you go. And the formula for gravitational potential energy is mass times gravity times height. No 1/2 this time, just mass times gravity times height. And there are two ways I'm going to write gravitational potential energy. It could be PE subscript G. That's the way, I guess if you're going to do physics in college, this is how you're going to see it. But I might just use GPE as well. And that's probably what I'm going to be using here in high school. But just know that if you do take physics in college, you might see it like this. The same thing, honestly. It's just this is more easier to read. So GPE, gravitational potential energy, since it is an energy, it's also measured in joules. Mass is still measured in kilograms. And gravity is always 9.8. It's never going to change unless we're on a different planet. But don't worry about that. We're not going to do that this unit. So it's just always going to be 9.8. So you always know G is 9.8. And then your height is going to be measured in meters. Here's another triangle if you like to use it. We're not going to solve for mass, gravity, or height today. We're just going to be solving for potential energy of gravity. So the relationships, just like kinetic energy, everything's directly related to potential energy. So the heavier something is, the more mass it has, the more gravitational potential energy it has, which makes sense, right? You need to put more energy into lifting something that has more mass. And height is also directly related. So the higher up you go, the more gravitational potential energy you're going to have. Again, it takes more energy to fall down farther than it does just to fall down a little bit. So this is the second problem I'm going to show you today. Don't worry, again, tomorrow we're going to go through more formulas. So find the gravitational potential energy of a 65 kilogram person, so that's my mass, sitting on a diving board that is 3 meters high. That's my height. And I'm looking for my gravitational potential energy. My G, P, E. This is hard to write. Tomorrow I'm just going to do it on paper. I can't do this on the computer. This is hard. So G, P, E is equal to mass times gravity.
Mr. Vino, don't you have that like little annotate thing for your for Zoom? It's like way faster.
This is what I'm using.
Oh, it is? Oh,
Yeah,
okay.
look.
I was like,
I have it up right here. Oh, you can't see.
uh,
Did I break it?
but you can like type text and stuff. That's what my oh yeah, you are. That's what my geometry teacher uses, and it's like way faster. She like types it out and arranges it.
I guess I could do that. I'll figure that out later though. Right now I just want to hurry up.
It's early release, I don't need to think.
Yeah. I even bought that cool like stylus pen where I can just write. But of course I left that at home and I just keep forgetting to bring it. All right, so when you're multiplying mass, gravity, height, that's all you have to do. It's just multiply. You're gonna end up getting something around, I think I used 9.81, but it's 191295. It might be a little bit less because I used 9.81 when I solved it. Oh, yes, I will show you the schedule later. I emailed the schedule to everybody, by the way. It's in your email, but I will still show you the picture later when we're done with this. So again, pretty easy, not too hard. Tomorrow, again, we'll go through solving mass and height. I won't have you solve for gravity because, like I said, gravity's always 9.8. Now we have elastic potential energy. These are going to be for objects like springs, rubber bands, wires or cords. Like if you're ever playing guitar, that's elastic potential energy. In order to stretch or pull something or to compress and push something, you need to do work. Before the spring is released to return to its original state, it requires elastic potential energy. So elastic potential energy is the energy stored by compressing or pulling an object. And the formula is going to be 1/2 the spring constant times the distance squared. And we're not going to learn this formula this year, so don't worry about it, but I just wanted to talk to you about it. So again, anytime you're pulling apart a spring and you're holding it, that's elastic potential energy because it has the potential to go back to how it originally was. Just like when you're strumming a guitar and the wires are moving, it has the potential energy to go back to being straight, to not making any sounds. But again, fortunately, we do not have to do the formula this year.
Yeah.
So we don't need to learn this. We don't need to do this. We don't need to do this. Now you just have to do your discussion questions and you're done.